When last we met, we were trying to integrate a pretty nasty integral, sine to the sixth of x over 3, and we expanded it out using a power-reducing identity and cubing a binomial, and then we got to this cosine to the third of something, of 2x over 3. And that made us sad, not only because the problem was so big, but we actually haven't learned how to deal with cosine cubed or sine cubed yet. So we're going to have to go back to our toolbox of trig identities, but this is not an obscure one like the power-reducing ones. We're going to use the Pythagorean identity, which is your favorite identity, right? Everyone's favorite trig identity is the Pythagorean identity. And you're going to say, but wait a second, this is a cube, not a square. Well, that's good, actually. When you have odd exponents, we can leave one factor for u sub. The remaining even number of factors can be rewritten using the Pythagorean identity. So how does that work? We're going to leave one factor out for u sub, so cosine of x is going to be the one factor, and what's left is two more factors, so cosine squared of x dx. All right, so I think everyone will admit that these are the same, and now that we can use the Pythagorean theorem on this even exponent, we can replace cosine squared of x with 1 minus sine squared of x dx. Now, when I say leave one factor behind for u sub, that doesn't mean that I'm going to let u equal this. I want to let u equal the other one so that du equals this. When I say the other one, I mean sine in this case, right? So if u equals sine of x, then du equals cosine of x dx, which is great because cosine of x dx can get replaced with a du. And the only thing that's left is 1 minus sine squared of x, but that's 1 minus u squared. And that's a very easy integral, right? We get u minus 1/3 u cubed, or sine of x minus 1/3 sine cubed of x plus c. So that's a pretty nice problem, not so nasty. And then what's going on here? All this fraction business. This is terrible. But don't forget that we have other techniques, right? Like, for example, notice that if we look at this guy right here, that might be scary. But if you think about its derivative, wait a second, the derivative of 1 over x is negative 1 over x squared. Oh, okay. So we can actually make this a little bit prettier if we start off with a useful u sub of 1 over x. That means that du equals negative x to the negative 2 dx. Or, I don't know, I guess we'll go ahead and solve for dx on this one. Negative x squared du equals dx. So right off the bat, we can get rid of that 1 over x by saying this is sine to the fifth of u divided by x squared times dx, but dx is negative x squared du. So good deal. The negative gets pulled out front. The x squareds are gone, and we have sine to the fifth. All right. So that's just an extra little piece to remind you that we could have multi-steps here, but we still have to deal with this to the fifth. We dealt with to the third power. Now we have to deal with to the fifth power. Well, leave one factor out for u sub. So we've got negative the integral of one of the factors is sine of u. The other even number is 4 of them, right? So we have sine to the fourth, but I don't want sine to the fourth. I want sine to the second. So I'm going to divide that 4 by 2 and get 2 remaining, right? So sine to the second squared is sine to the fourth. Sine to the fourth times sine is sine to the fifth. All right, so what that gets us is sine of u, again reserved for the u substitution coming up. I guess it will be v substitution because we already used u. And then sine squared of u can be rewritten using the Pythagorean identity. This sort of problem with odd exponents always uses the Pythagorean identity. And this time we're going to have to square that. So yeah, I think probably the best thing to do is square this out, unfortunately. I'm going to leave this sine of u factored out because that's going to go away pretty soon anyway. But I'll go ahead and square that binomial. 1 minus 2 cosine squared of u plus cosine to the fourth of u. And again, we're reserving this for the u substitution. We want to make sure that whatever we pick for u, its derivative gets rid of the sine. So we better pick cosine of u. Whoops, let's not use u. Where's my button? Here we go. Let's try v substitution. That means that dv equals negative sine of u du. Oh, we've got the negative sine of u du. All of those get replaced with just a du. So we got the integral of, whoops, not du, sorry. This should be a v. It's hard not to use a u there. So we've got 1 minus 2 times the cosine squared of u is v squared, plus cosine to the fourth of u, which is v to the fourth. And again, the negative sine of u du gets replaced with a dv. So the integration here is, well, it's with respect to v, so 1 turns into v, and we've got 2/3 v cubed, inverse power rule, and 1/5 v to the fifth. All right, well, there's my answer, except it's in the wrong variable. We got to sub back the v to u, so instead of v, we'll have cosine of u. But wait a second, u is not part of our original problem. U is equal to 1 over x. So we got cosine of 1 over x minus 2/3 cosine cubed, right, cubed, of 1 over x plus 1/5 cosine to the fifth of 1 over x plus c. All right, so good times here. 2 u substitutions along with Pythagorean substitution, and we get there. Okay, this next one's going to be pretty much the same deal. This time we've got a u value of e to the x because its derivative is e to the x. So if we let u equal e to the x, du equals e to the x dx. So that can rewrite this as the integral, well, e to the x dx is just du. So we have sine to the seventh of u du. Again, that extra little piece for the u substitution just gets us to a place where we have a trig function raised to an odd power, right? So again, leave one factor behind for u sub purposes. And this time we have 3 sets of 2 factors, right? 2 times 3 is 6, 6 plus 1 is 7. So you see where this is going, perhaps. We're going to replace the sine squared of u with 1 minus cosine squared of u, but we do have to cube that binomial. Pascal's triangle, anyone? So we've got sine of u times 1 minus 3 cosine squared of u plus 3 cosine to the fourth of u plus, minus rather, cosine to the sixth of u du. All right. So remember, we want a u value, a v value, a v value that differentiates to sine of u. So v is going to equal the cosine of u, so that dv equals negative sine of u du. We don't have the negative here that we had on this last problem, so that means we're going to want to include that negative in here. The sine of u du goes away, turns into a dv, and we have 1 minus 3v squared plus 3v to the fourth minus v to the sixth dv. The actual integration is not so bad. It's just inverse power rule, right? We've got negative v, we've got positive v cubed. That's fun. We've got negative 3/5 v to the fifth, plus, you have to remember to flip all the signs, right? 1/7 v to the seventh, plus c. So this final answer here, if OneNote lets me scroll to the right, I'll have to use some horizontal space here. V is the cosine of u. U is e to the x, so v equals cosine of e to the x. So minus or negative cosine of e to the x, and yeah. We'll go ahead and finish this up. We get plus cosine cubed of e to the x minus 3/5 cosine to the 5th of e to the x plus 1/7 cosine to the 7th of e to the x plus c. Whew. Your hand gets a workout on these problems.